In sections 5.2, 5.3, and 5.4, we're going to be looking at probability rules. So these are going to be rules that we can use that will help us figure out what a probability is without having to list the entire sample space when doing so. We're going to start in section 5.2, and there we're going to be looking at the addition rule, and we're also going to be looking at complements. So we start by considering whether or not two events are mutually exclusive or disjoint. So two events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive events. In other words, the two events cannot happen at the same time. Let's say I'm drawing cards out of a standard deck of playing cards. If I am going to draw one card out, the event drawing out a heart and the event drawing out a diamond are mutually exclusive. It's not possible for those two events to happen on the same card. You can't get a heart and a diamond on the same card. In the same way, I draw a card, it can't be a king and a queen at the same time. So the event drawing a king, the event drawing a queen, those are mutually exclusive. But on the other hand, if I draw out a card and I'm curious about whether the card will be a heart or an ace, well, those two events are not mutually exclusive because it is possible to draw out a card that is both a heart and an ace at the same time, the ace of hearts. So again, we're considering those kinds of events that are disjoint, not the ones that are not disjoint yet. So we're going to be looking at events that are disjoint. So again, the two events can't happen at the same time. And so we have the addition rule for disjoint events. If E and F are disjoint or mutually exclusive events, then the probability of E or F occurring is equal to the probability of E occurring plus the probability of F occurring. So for example, suppose a single card is selected from a standard deck of playing cards. Compute the probability that the card will be a king or a queen. Compute the probability the card will be a heart or a diamond. So in part A, we want to know what is the probability if I select a single card that it will be a king or a queen. So what we're saying here with this addition rule is that since the events drawing a king and drawing a queen are disjoint, then all I really have to do is figure out what is the probability of drawing out a king, what is the probability of drawing out a queen, and add those two things together. Now, the probability of drawing out a king is 4 out of 52 because there are 4 kings in a deck of 52 cards. And if you're not familiar with playing cards, then these are the 52 cards and 4 of those are kings. Plus, the probability of drawing out a queen is also 4 out of 52. Again, we have the 52 cards, and here are 4 queens, so 4 out of 52. So if I just add those together, 4 plus 4 is 8, so we get a probability of 8 out of 52. Now, typically when we're dealing with fractions, we're going to simplify those. So 8 and 52 can both be divided by 4. 8 divided by 4 is 2. 52 divided by 4 is 13. So we have a 2/13 probability. So again, if the two events are disjoint, really all you have to do is find the two probabilities and add them together. B, compute the probability that the card will be a heart or a diamond. Well, probability of heart or diamond. Again, hearts and diamonds, those are disjoint events. They're mutually exclusive. They can't happen at the same time. So that's just going to equal the probability of a heart plus the probability of a diamond. The probability of drawing out a heart, well, again, if you're not familiar with playing cards, there are 13 hearts in the deck of 52 cards. So the probability of drawing out a heart is 13 out of 52. There are 13 diamonds in the deck of cards. So the probability of drawing a diamond is 13 out of 52. 13 plus 13 is 26. So we get a probability of 26 out of 52. And that will reduce to 1/2. Both can be divided by 26. And so we have a 1/2 probability of drawing a heart or a diamond. So pretty straightforward. If we have disjoint events, we can just add their probabilities to get the probability of one or the other occurring. Now, what if they're not disjoint? For any two events, E and F, the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F both occurring. So again, notice this is the probability of E or F occurring. That's going to just equal the probability of E occurring plus the probability of F occurring minus the probability of both occurring at the same time. So an example of that. Suppose a single card is selected from a standard deck of playing cards. Compute the probability that the card will be a king or a heart. Now again, the issue here is that kings and hearts, those two events, are not mutually exclusive. So what might be a temptation is to use the same rule we just used up here. So we would say the probability of king or heart. And again, the temptation might be to just add those together. The probability of king plus the probability of heart. But here's the issue with that. So I'm not finished here. I'm going to come back and finish this. The probability of drawing a king, well, there's 4 kings out of 52 cards. The probability of drawing a heart, there's 13 hearts out of 52 cards. The trouble with just adding these two together is that the king of hearts is included in these 4 kings. The king of hearts is also included in these 13 hearts. So the king of hearts is being counted in both of these probabilities. So because of that, we have to subtract off one of them so that we don't have a double count. So we're going to subtract away the probability of being a king and a heart at the same time. So again, we're doing that so that we're not double counting. Now, the probability of being a king and a heart at the same time, well, there's only one card that's a king and a heart at the same time. That's the king of hearts. So again, because the king of hearts is being counted both in the 4 and in the 13, we're subtracting off one so that we're removing the duplicate. So that gives us 4 plus 13 is 17 minus 1 is 16 out of 52. And we can reduce that. 16 and 52 can both be divided by 4. 16 divided by 4 is 4. 52 divided by 4 is 13. So there is a 4/13 probability that the card that we draw out will be a king or a heart. So we just have to be careful here, again, to make sure we're not duplicating. So take a look at this next example. Working couples. A guidance counselor at a middle school collected the following information regarding the employment status of married couples within his school's boundaries. So we're looking at married couples within the school boundaries. That's what we have here. So single people aren't included in this data, only married couples. So what do we have here? This table of information that we have right here is called a contingency table, or sometimes it's called a two-way table. Now, what that means is that there's really two variables of information included in this table. If you look at the rows, in the rows of this table, we have information regarding who's working in the married couple. So is the husband only working? Is the wife only working? Or are both working? It seems to me there could be a fourth category there. It seems to me that neither working could be a possibility there as well, but apparently not within this particular school district. Everyone has at least either the husband or the wife working or both. So again, that's the row variable. That's the information in the rows. In the columns, we have another variable. We have information about how many children that's under the age of 18 that this married couple has. So we have 0 children, 1 children, 2 or more children. Okay, and then of course we have the totals as well. So we're supposed to use this information to answer the following probabilities. What is the probability that for a married couple selected at random, both spouses work? So I'm going to come up here just to give myself some room for all of these. So we're looking for the probability that both work. So how am I going to figure out that probability? Well, I need to figure out how many couples there are where both spouses work. And if I look at this particular table, it looks like there's a total of 1,149 couples where both spouses work out of 1,700 couples altogether in this data. So that's just going to be 1,149 out of 1,700. Now, when we have fractions like that, we're usually going to change them to decimals. So 1,149 divided by 1,700, that is approximately 0.6759 if I round to 4 places. So this is approximately 0.6759. What is the probability that for a married couple selected at random, the couple has 1 child under the age of 18? So now we're looking at the probability of 1 child. It's 1 child. Well, now I'm looking at this variable, right? So altogether, there were 353 couples that have 1 child out of the 1,700 couples. So that probability is simply 353 out of 1,700. So 353 divided by 1,700, that is 0.2076 if we round to 4 places. 0.2076. Part C. What is the probability that for a married couple selected at random, the couple has 2 or more children under the age of 18 and both spouses work? Now we're turning it up a little bit here. So for C, we want to know the probability of 2 or more children and both work. So notice this is an and question. We need to meet both conditions. So to figure out this probability, I'm going to figure out how many couples are there that have 2 or more children and both work. Well, so I'm going to go to this column and this row. There are 370 couples who have 2 or more children and both work out of the 1,700 couples. So this probability is going to be 370 out of 1,700. And so if I divide that, that is 0.2176. So the probability that both the couple have 2 or more children and both work is 0.2176. D. What is the probability that for a married couple selected at random, the couple has no children or only the husband works? So the probability of 0 children or only the husband works. Now this is an or question. So in order to figure out this probability, I'm going to add. I'm going to use an addition rule. So I need to figure out, are the events having 0 children and only the husband works mutually exclusive or not? Are they disjoint, in other words? If they are disjoint, then I just need to add them together, the 2 probabilities. If they're not disjoint, then I'm going to add the 2 probabilities together and subtract the probability of 0 children and only the husband works. So, are the events 0 children and only the husband works mutually exclusive? Well, no, they're not. If you look right here, we have 0 children and only the husband works. There's 172 couples that fit that category. So these 2 events are not mutually exclusive. They can happen at the same time. So what I'm going to do is I'm going to find the probability of 0 children, and I'm going to add the probability that only the husband works, and I'm going to subtract from that the probability of 0 children and only the husband works. So what's the probability of 0 children? Well, there are 788 couples that have 0 children out of the 1,700. So that's going to be 788 out of 1,700. What is the probability that only the husband works? Where there's 425 couples where only the husband works out of the 1,700 couples. But again, the problem with just adding those together is that in these 788 couples right here, 172 of them, only the husband works. In these 425 couples where only the husband works, 172 of them have 0 children. So if I just add this and this, that 172 is being counted twice. It's being added in both. So I have to subtract out the probability of both. And so I'm going to subtract out the 172 out of 1,700. So if I take 788 plus 425 minus 172, that equals 1,041. So this equals 1,041 out of 1,700. And if I do that division, then that's going to be 0.6124 if I round to 4 places. So this is approximately 0.6124. Now, when we have data like this, you could have also have figured out what this 1,041 is going to be by just adding up the 522, the 94, the 172, the 79, the 174. So you could have added up those 5 things, and that would also give you the 1,041. In this case, though, we're dealing with the addition rule, so I wanted to demonstrate how that addition rule works and why. The last question, part E, would it be unusual to select a married couple at random for which only the wife works? So there we're looking for the wife only works. Well, the wife only works, there's 126 of them out of 1,700. And if I take 126 and divide by 1,700, that is 0.0741. So is that unusual? This is not unusual. And it's not unusual because 0.0741 is greater than 0.05. So since this is not smaller than 0.05, that's why we would say this is not unusual.